This unit discusses two important topics: inversion of control and the model view controller pattern. In the early days of programming, developers thought in terms of procedural logic. Code was organized in terms of dividing the problem into smaller and smaller manageable chunks. And thinking along these lines led people to layer programs so the higher layers controlled the programming logic. The problem with that approach is that it increases the coupling of the application because applications were written with specific implementations in mind. If an algorithm had to be changed, at the very minimum, a massive recompile was required. We have already shown how in the preceding units, interfaces allow us to write an application that depends on behavior and not a specific implementation. We can take this one step further using the idea of inversion of control. Inversion of control pushes the details of the implementation to the lower layers of the application. And by doing so, it minimizes the coupling of the application because the application is held together through abstract definitions of behavior in an interface. When we replace one type of concrete class with another, there is no structural effect on the rest of the system because the dependency is on the interface that they both implement. Remember, however, we are talking here about minimizing inessential coupling. Obviously, if you replace one concrete class with another, there could be a huge effect on the system because the algorithms implementing the behavior could be widely different. It is important to emphasize this point. People often claim that using inversion of control or other laying techniques means that the system does not make assumptions about what other parts of the system can or should do. This is only true of inessential coupling. Parts of the system have to make assumptions about other parts of the system to which they are essentially coupled. In an accounting application, the reporting system can run without crashing, even though the journaling system does not work. The reports, however, will make no sense, and this is little comfort to the end user. So where are the concrete instances created? This knowledge has to exist somewhere. We have already seen examples of inversion of control in the previous unit. With the data mapping layer, we have used a factory to create the concrete class. This concrete class was passed as an interface to the constructor of the customer manager class. For the customer repository class, we create an instance in the customer manager class and pass the iDataMapper interface to its constructor. Now, instead of using a factory to achieve inversion of control, we can use a piece of technology called a dependency injection container. The container, rather than the factory, decides which concrete classes get created. A factory, no matter how sophisticated, is created at compile time, and the choices are limited by those decisions that exist in code. A container, as we will explain shortly, can allow for the decision as to which class is created occur at runtime. This would, for example, facilitate testing where you want to substitute a test class for the real class. The real class might work against a service that charges money or takes too long for rapid unit tests. A container might also allow you to inject code for a cross-cutting concern such as logging. This container is driven by a configuration mechanism that it uses to determine which classes to instantiate at runtime. Very often, the application as a whole is not aware that a dependency injection mechanism is being used. This then, of course, is the ultimate decoupling because the decision on instantiation happens at runtime. To illustrate how a dependency injection container works, this unit has a very simple example. It is designed to show you the essential features of what a dependency injection container has in order for you to understand when it's appropriate to use this mechanism. Our dependency injection container is implemented as a very simple plugin manager, the details of which we will discuss in the codecast. But basically, it has one method called loadType. And this method takes as an argument a string, which is the type that the application wants to load. The plugin manager then uses the configuration tables to look up what type should actually be loaded, and uses reflection to find the type, instantiates an instance, and returns it. So in our particular example, the code can use one data mapper, and the tests for the customer manager layer can use another data mapper. This works because the code only depends on the behavior of the iCustomerDataManager class, not a concrete application. And if you compare the two versions of the data mapper, the customer data mapper and the test customer data mapper, you will see that they implement the same interface differently. After analyzing this example, you can now see the problem with dependency injection containers. They introduce a large level of indirection at the cost of complexity. With such a container, it can often be difficult to figure out exactly which class is being instantiated. In a debugging session, you often cannot step through the configuration file, and stepping through the code in a real container to figure out what is actually happening can be quite difficult. On the other hand, it can be easier than writing factories and might simplify your application if used properly. Since using a dependency injection container allows you great flexibility in building tests for individual parts of an application, many developers feel dependency injection to be used throughout the application. To me, this is a judgment call. How much testing and code coverage versus code complexity you need is a trade-off compared with other project constraints, such as time, money, or the need to deliver functionality in a timely manner. Too much dependency injection complicates an application to the point where it can be hard to decipher what is going on. To me, dependency injection works best at component boundaries because that is where the flexibility in the system is needed and the fragility in the application exists. In the second unit of this track, we discussed what is meant by component boundaries. One of the most important isolation layers of an application is between the domain model and the user interface. Typically, user interfaces are hard to test, so separating the two makes it easier to test the business logic independent of the user interface. Further, an application might have multiple user interfaces for the same domain model. It also allows the user interface to evolve without impacting the domain model. The model view controller pattern is one of the most fundamental patterns for separating the user interface from the business logic in an application. Our initial application for this pattern will be in our console application. Now, the model has no user interface interaction, so it represents the business logic. The controller handles input events from the user interface, and the view represents the appropriate display of the model. This also keeps the UI level very small, making the business logic easy to test and evolve without affecting the business logic. In the Codecast, we will take a look at the details of how we've implemented Model View Controller. And we will build on this in the next unit to convert the UI to a web app, keeping the model intact. And then when we introduce web services, the web app will not have to change because the model will be the one that is affected. So to summarize, we've looked at inversion of control as a means to minimize the coupling application, and dependency injection as an example of inversion of control to show how to make decisions at runtime about which objects to instantiate. The model view controller pattern decouples UI from the business logic and allows for flexible testing and evolution of the application.